Hello friends, good afternoon and welcome to EduSet Live Lectures. Dear friends, as you know that we've started a series on phase equilibria and today we're conducting yet another lecture in the same series. In today's lecture, we will continue with solutions and it will be fourth part in solutions. To discuss this topic, we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you so much, Amrit. First of all, I wish very good afternoon to all the dear viewers. Dear viewers, as you have been apprised of, that in the subject matter series of phase equilibria, we are continuing with the topic matter of solutions, and this has been the fourth lecture in the series on the topic matter of solutions. So today we are going to talk about, first of all, the vapor pressure versus composition curve. We will try to revisit them with a view to an understanding of how the composition of the system varies and what it is related to. Then we will derive the lever rule and we will try to see what way the lever rule is helpful to all of us. And then after that we will carry on further discussions on the sequence of effects which get produced upon decrease in pressure on the overall system, and following which we will be having numerical techniques that is very important in dealing with this subject matter, and it is these set of numericals with solution of them achieves a lot of understanding in the subject matter of physical chemistry. So with that brief introduction to what we are going to cover today, we are going to start with the vapor pressure versus composition curve. If you remember, if we were having a liquid solution which is a binary solution, that means there are two components which are present in the solution and both the components are in liquid phase, though they go to form a liquid solution. And liquid solution which when gets result, one component is less volatile and the other one is more volatile. And you can say over here, you can take any terminology, either you can say component A or component B, or you can say component 1 and component 2. So here component A or component 1 is just been the same and component B or component 2 is just been the analogous terms. So component A means solvent, in the same way component 1 means solvent. If component B is taken, that means we are talking about solute. Component 2 also means solute. So right, so if you would just have a look at this phase diagram once again, which represent the binary ideal liquid system, then you will see that there is a liquidus curve which is a purple color curve over which is being shown over here, which is a straight line, and a blue color curve is called vaporous curve. These are called so because these relate the total vapor pressure of the solution with respect to composition in liquid phase and composition in vapor phase respectively. So accordingly these curves are called liquidus curve, the straight line curve, and the vaporous curve is a curve which is having a curvature. And these are governing equations which help determine the total vapor pressure with respect to composition in liquid phase, that is represented by letter small x, and composition in vapor phase which is represented by small letter y. So here x1 means amount fraction or mole fraction of component number 1 in liquid phase, and small y1 means amount fraction or mole fraction of component 1 in the vapor phase. Alright, so it means total vapor pressure is related to P2 naught plus P1 naught minus P2 naught bracket close x1, that is total vapor pressure in this straight line equation is related to composition in liquid phase, or in other words the amount fraction of component 1 in liquid phase, and whereas in second equation total vapor pressure is related to composition in vapor phase by represented by small letter y1, or in other words the mole fraction of component 1 in the vapor phase. Having said so, now it is important to understand that if we have a pressure which is being applied onto the system, which according to which there should be fixed composition of liquid and vapor phase, and suppose at this pressure where the pointer is pointing out, at this pressure point when we draw a parallel line to x axis where it meets liquidous curve at point A and vaporous curve at point B, and therefore these point A and point B represent the amount fraction of component A, you can say, or you can say amount fraction of component 1 in the liquid phase and in the vapor phase. Now the point is, so long as, first of all it is very important to note that this curve or this graph or this diagram is drawn under condition of constant temperature. This is very important to note. Now beyond that, it is further important to note when the temperature is kept constant, the equilibrium pressure is a function of the composition in liquid phase, composition in the vapor phase as well. Both of these compositions are drawn on the x axis. Also drawn on the x axis is the amount fraction of component A or component 1 in the overall system. So therefore x axis represent composition in liquid phase, composition in vapor phase, as well as composition in overall system. And mind you, the composition is represented by the term amount fraction, and amount fraction of a particular component, as you know, varies between 0 and 1. That is why you observe two vertical lines being drawn at 0 and 1, which means this graph is a close-ended graph. Alright, having said so, if it means that when at a fixed temperature, when the pressure of the system is kept constant, then the composition of the liquid and vapor phase, if these two phases are present in equilibrium with each other, should be fixed. And this fact is in accordance with the phase rule, because the phase rule equation says degree of freedom equal to C minus P plus 2, and C is number of components, which is 2 here, P number of phases, if there is liquid and vapor phase, so again we have 2 phases, plus 2, it means degree of freedom is 2. One is being used up in specifying the temperature of the system constant, because we have drawn this phase diagram under condition of constant temperature. So we have made use of 1 degree of freedom. So now we are left with only 1 degree of freedom, that is pressure. That means if you fix the pressure, then the composition automatically gets fixed, and that is why at a fixed pressure represented by this point where the pointer is pointing out, at this pressure point A and point B represent the composition in liquid and vapor phase. But the question arises, what about the composition of overall system? The composition of overall system should lie anywhere in between this line segment AB, that is anywhere between the 2 points A and B, and the composition of overall system is represented by point O. This point O can be anywhere close to point A or close to point B or somewhere in between these 2 points A and B. But now question arises, who determines as to what is the overall composition of the system? This composition of overall system, mind you, is basically depend upon the relative amounts of the two phases which are present in the system. What we mean by saying so, the relative amounts, it means that what is the total number of moles in the liquid phase and what is the total number of moles in the vapor phase. If we take the ratio of these two total number of moles in both these phases, this represent a quantity which represent the relative amounts of two different phases, and this relative amounts of two different phases basically on the basis of which the location of this overall state point O is determined. So let me once again tell you, this point O is basically called given the designation of representing the overall state point of system, whereas small letter point A, this represent the state point of the liquid phase, and the small letter point B, this represent the overall state point of vapor phase. Overall state point means the point O represent composition in the overall system, the point A represent composition in liquid phase and point B represent composition in vapor phase. This we should understand from this graph which we have shown you just a little while ago. Alright, having said this, now it is time to understand that on how we can determine this relative amounts of two different phases. Is there any logic? Is there any formulation? Is there any formula? Is there any mathematical equation with the help of which we can determine this relative amounts of two different phases? The answer to this question is yes, we can do so just by merely having the phase diagram drawn present in front of us. We can, just by looking at it, we can, with the help of a scale, we can measure certain distances and we can obtain the relative amounts. For example, if you just see N liquid, here N liquid is just the symbol which represent the number of moles, total number of moles in the liquid phase, and whereas N vapor represent the total number of moles in the vapor phase, which is equal to, here it is written OB by OA, but it should be, yes, OB by OA. What it does mean, if you see it very carefully, this is called lever rule. The ratio of two line segments, that is OB is to OA, is basically equal to ratio of number of moles of the liquid is to vapor phase. But the question arises, how we have arrived at this formula? How we can say that this rule is basically something which helps us to know relative amounts? So we will go about to derive this formula. So on the basis of which we can say yes, we have derived it and we can make use of this formula. And this formula is basically describes lever rule. And according to the lever rule, what we have, lever rule is just like, if you see point O, you can think of as the fulcrum of a lever onto which two different masses are tied at two different distances. From point A at distance OA, there is a mass is tied at point A, and also from point O at a distance OB, a mass is just being tied at point B. So point O represent as the fulcrum of a lever, and we can say that it is the number of moles or amount of substance in the liquid phase multiplied with the length of line segment from overall state point to the liquid phase curve, that is this purple curve or a straight line curve. This line segment is OA. This multiplication should be equal to, as per the balance, OB should multiply with the number of moles in the vapor phase, which we when rearrange, what we get is N liquid by N vapor equal to OB by OA. Alright, if we want to derive this phase rule, what we need to do? Just have a look at it. You see, if we say N1 liquid, if we say N1 liquid, N means number of moles, subscript 1 means of component 1, comma liquid means in the liquid phase. So this N1 liquid symbol represent moles of component 1 in liquid phase, whereas N1 vapor similarly represent number of moles of component 1 in vapor phase, not in liquid phase, but this time in the vapor phase, because in the subscript there is not liquid but there is vapor. Right, so N1 total, that means what is the total number of moles of component 1 in the overall system, that is equal to number of mole of component 1 in the liquid phase plus the number of moles N1 in the vapor phase. So therefore N1 liquid plus N1 vapor equal to N1 total, that is total number of moles of component 1 in liquid and vapor phase together, because there are only two phases. So beyond that there will not be component 1 would be present anywhere in the system, would be present in liquid and vapor phase only. So therefore N1 total represent total moles of component 1 in liquid and vapor phase together. So N liquid, now this N liquid symbol represent total number of moles of component 1 as well as of component 2 in the liquid phase. Similarly, N vape represent number of moles, total number of moles of component 1 and 2, both these components in vapor phase. Alright, so N total equal to N liquid plus N vapor. What this means is, If we now add total number of moles in the liquid phase and total number of moles in the vapor phase, this addition leads to a quantity called N total, which means total moles or total number of moles of both the components in the overall systems. I hope this symbolic representation is clear at this point of time, because we will make use of this symbolic representation in our manipulation of during the derivation of the formula for the lever rule. Having said so, now just have a look at this diagram once again. This point now not O but A represent in this diagram, point A represent fulcrum of the lever and point L represent the distance AL from the overall state point to the liquid phase, and this from this point A, which represent fulcrum of the lever, from this point the distance AV represent the distance of overall state point of the system to that of the vapor phase composition. So, we can now apply the lever rule and can derive the formula of lever rule for this diagram. Now, what way we will go to describe it, we will go to derive it, just have a look at this. Now, the symbolic representation which I just described you can be made use of to derive three things. One is amount fraction of component 1 in overall system, that is represented by symbol, this where this pointer is pointing out to be. You can just make a note of this symbol. This is represented by symbol capital X1, and this equal to what? Now, this capital X1 means the amount fraction or mole fraction of component 1 in the overall system. So, this can be calculated as number of moles of component 1 in the overall system to that of total number of moles. So, that this capital X1 is equal to N1 total, which represent the number of mole of component 1 in the overall system, divided by N total, which is nothing but the total number of moles of component 1 and 2 together in the overall system. Similarly, small x1 represent the amount fraction of component 1 in the liquid phase. So, therefore, how we can calculate it? We can take the ratio of number of moles of component 1 in the liquid phase to that of total number of moles of component 1 and 2 together in the liquid phase. So, this small x1 equal to N1 liquid divided by N liquid. Similarly, small y1 represent amount fraction of component 1 in the vapor phase, because symbol y is been chosen for the vapor phase. So, small letter y1 equal to N1 vapor by N vapor, which means number of moles of component 1 in the vapor phase, total number of moles of component 1 in the vapor phase to that of total number of moles in the vapor phase of both component 1 and 2 together. So, now we can make use of these distances of overall state point, that is A, to that of liquid phase, that is represented by line segment AL, and this line segment AL can be calculated using these formulas of amount fraction of component 1 in liquid phase, vapor phase and overall composition, just by taking the difference of coordinates of point A and coordinates of point L. If we take the coordinate of point A, what it represent on the x-axis? It represent, you can see on in the diagram, it represent capital X1, which means overall state point of the system, and therefore, this point represent amount fraction of component 1 in the overall system. So, the coordinate of this point on the x-axis of point A is X1, capital X1 sorry. So, this capital X1 is been here, less the coordinates of point L, which represent on x-axis by small letter x1, that is amount fraction of component 1 in the liquid phase. That is how we can determine the length of line segment or the magnitude of length of line segment AL equal to capital X1 minus small x1. Similarly, we can also determine magnitude of the length of line segment AV by taking coordinates of point V less the coordinates of point A. So, we get small y1 minus capital X1 as the length of line segment. So, we need not measure, please appreciate this point here, that we need not measure with the help of scale on the diagram being drawn which is present in front of us, we need not measure these distances using a scale, rather we can make use of the coordinates of these points, which is represented by number of moles of component 1 in the overall system, in the liquid phase and in the vapor phase. So, easily we can calculate lengths of line segment AL and AV. Alright, now what is this AL? AL, if you see it, is equal to capital X1 minus small x1, and capital X1 equal to N1 total, that is total number of moles of component 1 in the overall system, to that of divided by N total, that is total number of moles of component 1 and 2 together in the overall system, minus small x1, and small x1 as you have seen earlier equal to N1 liquid by N liquid. Similarly, AV equal to N1 vapor by N vapor, that represent Y1, minus capital X1 equal to N1 total by N total. Now, what we can do is, we can, if you see, we have represented point A. If you see in the diagram, we have represented the point A as the fulcrum of the lever. So, it means any mass which is tied to this length of line segment AL will be multiplied by with this distance. So, therefore, this is the of amount fraction of component A. So, therefore, we can multiply this number of moles of component total moles in the liquid phase multiply with AL, and number of moles of all the substances in the vapor phase with AV, and these two should be equal. These two should be equal when there is a balance in the lever. Alright, so just we are having N liquid into AL equal to N liquid into this bracket term, and N vapor into AV equal to N vapor into again this bracket term, where the only difference between these two bracket terms is that one which is having the difference of coordinates of point AL of line segment AL, and here in this vapor phase curve, this has the difference of coordinates of point A and V. So, we can take this, we can subtract the two. When we do subtract the two, what we get is, by way of little manipulation, we get N1 total by N total into N liquid minus N1 liquid less the bracket term N1 vapor minus N1 total by N total into N vapor. Now, if we take this bracket term outside, because of the minus sign, signs gets reversed. So, what we get is N liquid AL minus N vapor AV equal to N1 total by N total. Now, this manipulation of the bracket term now leads to N liquid plus N vapor minus N liquid, N1 liquid plus N1 vapor. So, now basically the bracket term, if you look at it inside, N liquid plus N vapor is basically total number of moles of liquid phase and vapor phase together. So, we can substitute in place of this, we can substitute for N total. Whereas, the second bracket term, if you see, where we have N1 liquid plus N1 vapor, it means number of moles of component 1 in the liquid phase and in the vapor phase, which becomes equal to N1 total, that is number of moles of component 1 in the overall system. So, now here in this equation, N total gets cancelled in the numerator and denominator. So, what you have is N liquid AL minus N vapor AV equal to N1 total minus N1 total, that is equal to 0. That is what I was saying, when there is a balance in the lever, the two masses being tied onto the two sides should have the same weightage. That is how we get, and when there should be a balance, when there is an equilibrium being established between the two phases, that is what we represent a balance point. And therefore, N liquid AL minus N vapor AV equal to 0 and N liquid AL equal to N vapor AV. We can take, because we have taken this N vapor AV term to the right hand side, and when we once again rearrange it, what we get is N liquid by N vapor equal to AV by AL. If you can see it very carefully, so now lever rule, we can state it in terms of words as it is the number of moles of a liquid phase multiplied by the line segment, by the distance of line segment from overall state point to that of the liquid phase, that should be equal to number of moles of vapor phase multiplied by the distance of line segment from overall state point to that of the vapor phase when equilibrium is established. When we rearrange it, what we get is n liquid by n vapor, which is nothing but the relative amounts of the two different phases, that is n liquid by n vapor, that should be equal to AV by AL. So, we can also understand it in by way of a mnemonic that it is the number of moles of liquid to the vapor phase equal to the ratio of line segments from overall state point to the vapor phase to that of the liquid phase. So, having this discussion of the lever rule, we will try to find out what way we can apply this and we can carry out, we can understand fractional distillation. Thank you. Alright, in this module we will try to understand the sequence of effects which get produced when we decrease the pressure on the overall system. So, now let us once again have a look at the vapor pressure versus composition curve of a binary ideal liquid system, and let us try to understand what effects gets produced and when we decrease the pressure on the system. So, for that we can have a look at this way on the vapor pressure versus composition diagram. You see, if we have the overall system which is represented by this overall state point A now. Now, the the question arises where this point A lies, this point where it lies in the liquid phase. As you can see, any point above this curve, purple curve or a straight line curve represent a liquid phase, and any curve below this curvatured curve represent a vapor phase, or a blue curve represent vapor phase, and any point in between these two curves represent two phase region, or in other words, because we are dealing with here liquid systems which are in equilibrium with vapor phase. So, we have here liquid vapor region, you can say. So, therefore, our point A lies in the liquid region. It means if we had mixed, suppose x moles of A with y mole of B, so total number of moles is x plus y, then amount fraction of the overall system would be represented by this point A by drawing a perpendicular on the x axis, and where this meets the x axis, this point now represent capital X, point capital X. This means capital XA, which is nothing but the amount fraction of component A or 1 in the overall system. Now, this lies in the liquid phase. It means we have in our system only the liquid phase. If suppose we decrease the pressure on the system, how we can decrease the pressure on the system? By carrying out expansion of the system. So, when we increase the volume, so the pressure gets decreased. So, when the pressure gets decreased, you can see that the overall state point will move along this vertical line, and ultimately when you continue to decrease the pressure, you could see where the pointer is moving, and when this reaches this point L on the diagram, it means now in the system you will have first trace of vapor which gets formed, or first bubble of vapor which gets formed. And you see what will be the composition of that vapor phase, as I have described earlier in our previous modules, that if you want to determine from a point the composition of the two different phases in equilibrium, then from that point you can draw a tie line, a horizontal line parallel to composition axis, where it meets the two curves. These meeting points represent the compositions of the two phases. Here we have liquid and vapor phase. So, point L you can see lies exactly on the liquidus curve. So, what it means, the overall composition and the composition of the liquid phase lies closely in coincidence with each other at point L, and the vapor phase point lies at this point, which is nothing but point V, where this pointer is pointing. You may just have a look there, this should be written over here V. And now you can see, it is important to note that composition of the vapor phase, although very small, a first trace or a first bubble being formed, but they have the amount fraction of component 1 in the vapor phase much greater, represented by symbol Y as compared to this capital X. And this is important to note that capital X is also small x at this point. If we decrease the pressure of the system further, then when the overall state point reach point A dash, then L dash V dash represent composition of liquid and vapor phase, and we can determine composition of liquid and vapor phase as X dash and Y dash. And once again, if we decrease the vapor pressure, the pressure on the system, then the overall state point reached point V double dash. Now it is important to note that here at this point we can draw a tie line which represent L double dash and V double dash as the points which represent the composition of liquid and vapor phase, and this V double dash now coincides with composition of overall system capital X, and X double dash is composition of liquid phase. This is what is represented as the sequence of effects which get produced when we decrease the pressure on the system. That is, when we decrease the pressure on the system, what way the system undergoes a change. First, there occurs a decrease in pressure of the system, and when it reaches a pressure at which the liquid phase comes in equilibrium with vapor phase, first trace of vapor, first bubble of vapor gets formed. When you continue to decrease the pressure on the applied pressure on the system, then what occurs is that continuously there is redistribution of amount of both component A and B, or 1 and 2 continuously occur from one phase, that is liquid phase, to that of vapor phase. An amount of vapor phase continuously increases, amount of liquid phase continuously decreases, and ultimately a point reaches where all the amounts have been converted from liquid phase to that of vapor phase, and at that point you have only last trace of liquid which remains. So, when we will attempt numerical questions, we will try to see what way this sequence of effects we can make use of to understand the calculation of various composition terms, various pressure terms, then we will try to see. Right. Now it is important also to note that isothermal fractional distillation, that is, isothermal means at constant temperature. So, this diagram is also drawn at constant temperature, if you remember. Then you can say that if you remember in the last two modules we had derived this rule which says that vapor which comes in equilibrium with the liquid phase has a greater proportion of more volatile component, or the more volatile component is richer in the vapor phase, or in other words, whenever a liquid phase is in equilibrium with the vapor phase, the latter is relatively richer in the more volatile component. Alright, if you we can have a look at what way we can carry out distillation process. In isothermal fractional distillation, what we try to do, if suppose we have a liquid, we have a system, in the system if we have only liquid phase and where this pointer is pointing, if this point represent the overall composition of the system and we have taken it to some higher pressure, when we decrease pressure at point O, somewhere in between, what happens at point O, the distribution of this overall system comes to two phases, liquid phase and vapor phase, and liquid phase composition is represented by point A and vapor phase is represented by component by point B on the diagram. Now these vapors is collected and is condensed. Condensed means pressure is increased onto them, so it makes another liquid. Again it is the pressure is decreased, and this liquid now reaches at this point where the pointer is pointing. At this point we have liquid L1 which comes in equilibrium with vapor V1, and this vapor V1 again is collected and is again compressed, and again pressure is decreased onto it. Then what happens is that again two liquid and vapor comes in equilibrium with L2 and V2, and if you note it very carefully, by way of this collecting these vapors and liquids separately, we are carrying out separation of the two components. In the vapor phase, component 1 is richer, and in the liquid phase component 2 is richer, because component 2 or component B is less volatile and component 1 or component A is more volatile. Continuously we can carry out this separation of vapor phase and liquid phase separately, and ultimately a stage reaches where liquid phase is only richer in the having the pure component B or pure component 2 or less volatile component, and in the vapor phase we have only component 1 or component A or the more volatile component. Right. Having said this way we carry out the isothermal fractional distillation, but this distillation process is usually not recommended for separation of liquid mixtures. Why this is so? Because this process is anyhow no doubt a cumbersome process, because variation in keeping the varying the pressure on the system is a very difficult and daunting task. Rather, varying the temperature is easy to carry out process. So therefore, this process is usually not recommended, but is certainly recommended for those liquid pairs which are susceptible to decomposition upon heating, upon change in temperature. So those liquids are carried out are subjected to separation by way of this isothermal fractional distillation if they are susceptible to decomposition upon heating or upon increasing the temperature of the system. So this process is usually not recommended, but is certainly recommended in certain liquid pairs which for which isobaric fractional distillation by way of heating the system does not work well. Alright, this distillation process or this vapor pressure versus composition curve we have discussed, this is only for the liquid systems where the liquid pair go to make a solution which is ideal in nature, and therefore this distillation process would also be applicable, this discussion would also be applicable to ideal systems only. But now the question arises, what were the known ideal systems distillation process and vapor pressure versus composition curve vary? The point is that if you remember in our previous module we have described if the vapor pressure is greater than that of what is predicted by Rolle's law, then we say the solution exhibit positive deviation from Rolle's law. And if the vapor pressure versus composition, in that situation vapor pressure versus composition curve, the equilibrium vapor pressure versus composition in liquid phase curve will not be a straight line, but will be taking a curvature which will be lying above that of the Rolle's law curve. On the other hand, if negative deviation occurs, the curvature will again be there, but with the vapor pressure will be slightly lesser than that of the Rolle's law curve. But it is important to note that the two curve does not meet if the vapor pressure versus composition in liquid phase and vapor pressure versus composition in liquid and vapor phase, these two curves do not meet if the deviations from Rolle's law or ideal behavior of a solution is not much. So in that case such liquid mixtures or such liquid pairs is called geotropic mixtures, which can be separated by way of distillation process. But there are certain liquid pairs for which deviations are much more, such that there is a very large maxima is observed in those liquid pairs vapor pressure versus composition curve. In those curves the equilibrium vapor pressure versus liquid phase composition and vapor phase composition curves do meet, and those liquid pairs you will see, we will discuss those liquid pairs. Those liquid pairs are called azeotropic mixtures, and we will discuss them later. But for the time being, it is important to note that those liquid pairs which do not exhibit very large deviation from ideality, so that a maximum occurs in the vapor pressure versus composition curve somewhere in between the two extreme compositions, then in that situation all the liquid pairs in the solution form can be separated by virtue of or by carrying out distillation, either isothermal fractional distillation or isobaric fractional distillation. Alright, so with this discussion now we carry out or we try to understand some numerical techniques. Let us take up some numericals. The first numerical says that if 3 mole of liquid A and 2 mole of liquid B were mixed to form a liquid solution, it means 3 mole of liquid A and 2 mole of liquid B is being mixed. So it means what he is giving? He is giving the composition of overall system. Mind you, whenever in the numerical, if somebody say that this mole of A and this mole of B is being mixed, it means he is giving you the total number of mole of A and B being mixed and is being present in the system. And whenever there occurs an equilibrium and only liquid phase occurs, the amount fraction of overall system will be equal to liquid phase composition, and when there is only vapor phase occurs, then the overall amount fraction of overall system becomes equal to the composition in the vapor phase. Or if there occurs an equilibrium, then the amount fraction of overall system will not be equal to either of the composition in the liquid phase or the composition of the vapor phase because of the Novolov rule. So in that situation, it is important to note that when in a numerical you are described that 3 moles of component A and 2 moles of component B, or for that matter any moles of component A or any mole of component B is being mixed, it means he is trying to give you number of mole of A and B, using which you can determine amount fraction of component A and B. This amount fraction will not be applicable to liquid phase, will not be applicable to vapor phase, but will be applicable only to the overall system, mind you. But when there is only liquid phase, so of course composition of overall system capital XA will be equal to small xa, composition in the liquid phase. And when there is only vapor phase in the system, then of course composition of overall system will be equal to composition in the vapor phase, that is capital XA equal to small ya. Alright, so now we move further and try to see what he asks in the numerical. 3 mole of component 3 mole of liquid A and 2 mole of liquid B were mixed to form a liquid solution, and the resultant solution was equilibrated at 353 Kelvin. What it means? The resultant solution, the solution which has been formed, that is brought to 353 Kelvin and is allowed to reach at equilibrium. And what is being recorded? A total pressure of 20.7 kilopascals. At equilibrium, a total pressure of 20.7 kilopascal is recorded. If mole fraction of A in liquid and vapor phase are this and are 0.578 and 0.649 respectively, it means what he has given is the amount fraction or mole fraction of component A in the liquid phase as 0.578 and in the vapor phase, or in other words the small ya, equal to 0.649. So calculate the number of moles of component A in the vapor phase. Now what is we are being asked? We are being asked to calculate number of moles of component A in the vapor phase. Now whenever a numerical is seen, what we should do? We should first of all try to analyze the data. What is being given to us? We are given composition in the overall system. That is equal to capital XA equal to since 3 mole of A was given, so 3 divided by total number of moles which is being added is 5, 3 by 5 equal to 0.6. So, capital XA is given as 0.6 and therefore, capital XB is equal to 0.4 only, because 1 minus capital XA equal to capital XB. Alright, what else he has given? He has also given the temperature at which this recording has been done. At 353 Kelvin, total pressure of the system is given, P total is given 20.7 kilopascal, and he has given composition in liquid phase, that is small xa 0.578 and small ya 0.649. So, we can analyze the data like this: total number of moles of A to mix to form solution 3 mole, and number of moles of B, this should be 2 here, not 3. So, a correction can be noted, and mole fraction of A in overall system, this is not 0.570, this is 0.6. So, again a correction, and this should be interchanged. Mole fraction of A in vapor phase is 0.649. So, here it should be 0.649, and mole fraction of A in liquid phase equal to 0.578. So, there it should be 0.578. So, now consider the formula. What is we are asked to determine? We are asked to determine number of moles in the vapor phase. So, we should concentrate at where the number of moles of component A in vapor phase occurs. This lies in the formula of amount fraction of component A in the vapor phase. So, therefore, Ya equal to NAV, number of mole of component A in vapor phase, divided by NAV plus NBV, that is total number of moles of A and B together in the vapor phase. Alright, so we will substitute the data in this. NAV divided by NAV plus NBV equal to Ya equal to 0.649, if you remember. I had just described in the previous slide. So, now therefore, NAV plus NBV equal to, we can take this denominator to the right side and we can take this 0.649 to the denominator over here. So, what we get is NAV, number of mole of A in vapor phase plus number of mole of B in vapor phase equal to NAV, number of mole in the vapor phase divided by 0.649. If you see, this formula is not sufficient for us to calculate NAV, what is we are asked in the numerical. Why? Because here in this formula we need to plug in the value of NBV, but we do not have the value of NBV. So, we should look at another formula which can give us the value of NBV. What that formula could be? That formula can be obtained in a way, just have a look. Now, consider the formula. What else we are given? We are given amount fraction of component A in the liquid phase also. So, this small xa equal to Na liquid, that is number of mole of component A in liquid phase divided by Na liquid plus Nb liquid, that is number of mole of component A in liquid phase plus number of mole of component B in liquid phase. But whatever is the number of mole of component A in the liquid phase, that is equal to total number of moles of component A present in the system minus number of mole of component A in the vapor phase. So, in place of number of mole of A in the liquid phase, we can write Na total number of moles of component A minus NAV, that is number of mole of component A in the vapor phase. So, you can see similarly we can do in the denominator also, we can write NaL, in place of NaL we can write Na total minus NAV, and in place of NBL by NB total minus NBV. So, if you can see, we are also given small xa, we are given Na total number of moles we are given, because we have been said that 2 moles of B and 3 moles of A have been mixed. So, Na, but we are not given NAV, we are asked to determine NAV. Again here in this formula, again if we plug in the value, if you notice, we are again having 2 variables, that is NAV and NBV, whose value we need to plug. We can rearrange this formula and what we get is 0.578, that is small xa. So, please see xa we have substituted for 0.578 and A total 3 moles we are given in the numerical value, NAV is just like that, and Na total equal to 3 mole minus NaV divide by 3 mole minus NaV plus 2 mole minus NbV. So, again we have this formula where we can rearrange, and if you see here we have NaV plus NbV. So, the equation we had developed earlier from the first formula, that is NaV plus NbV equal to NaV by 0.649. So, now we can substitute in this formula the second formula B, which we have got now, the equation B which we have got now. Here in place of NaV plus NbV we can put NaV divided by 0.649. Now, you can see we have this has led to an equation where we have only NaV as one variable, all other things are just the data set or the values, numeric values. So, we can manipulate this equation and ultimately we can get NaV, number of moles of component A in the vapor phase. Alright, we can attempt another numerical and we can have we can see what occurs in this numerical. And it says that at 353 Kelvin temperature is constant at fixed temperature. So, what we are trying to say, he are trying to ask us to look at vapor pressure versus composition diagram. The vapor pressure of two pure liquids A and B are 22 kilonewton per meter square and 1700 Newton per meter square respectively. So, what we are given Pa naught and Pb naught. When 3 mole of A and 2 mole of B were mixed in a cylinder with a movable piston, the system was allowed to arrive at equilibrium at 353 Kelvin and a total pressure of 20 kilonewton per meter square. So, P total is also given to us. So, calculate the composition of vapor phase in equilibrium with liquid phase. So, you just see some student try to bring a mistake here. They say that liquid A 3 mole is been mixed with liquid B 2 mole. So, total number of moles is 5. So, 3 mole divided by 5 mole equal to 0.6, and therefore, amount fraction of component A in the liquid phase becomes 0.6. This is not so. I have already told you whatever this number of moles are given, this can be used at best to determine the composition in the overall system, that is capital XA, but not small xa. This point one should look at. Now, just have a look. We are given Pa naught 22 kilonewton per meter square and Pb naught as 1700 Newton per meter square, but mind you that we should convert it to kilonewton per meter square so that both these have same units. So, we get 1.7 kilonewton per meter square. We can rearrange the total pressure versus composition in liquid phase formula to get composition in liquid phase as XA equal to P total minus Pb naught divided by Pa naught minus Pb naught. You can see now all these values Pb naught, Pa naught, P total are given. So, we can easily calculate small xa, and therefore, small xa comes out to be 0.85 and xb small xb equal to 0.15. Now, in order to determine composition in vapor phase, we get Pa by P total according to Dalton's law of partial pressure. So, Pa equal to xa Pa naught divided by P total. Xa we have just calculated 0.85 into Pa naught divided by P total, what is being given to us. So, 0.93 becomes the composition in vapor phase. So, in this way, analyzing the data in the given numerical, that is very important, and understanding which formula to apply at. Once we have this sequence in our mind of formula to be applied and the analysis of given data completely, we can easily attempt numericals. So, on that note, we will carry out solution to some other numerical techniques, and also we will try to see temperature versus composition curve in our subsequent modules. Thank you so much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Kumar for coming here and delivering this wonderful lecture, and thank you dear friends for watching our lecture. Stay tuned and keep watching. Thank you.